All right, everybody, welcome to our first online webinar for EV3 Software Workshop for Robofest 2017. I'm Professor Keith Bozen. Do some things in the chat window. I unfortunately will not be checking the chat window heavily because if I look at the chat window a lot, it distracts me from paying attention to the webinar. But occasionally I'll look over there and see if there is something going on. If you have any questions, post them there and we'll try to get back to them. I'll stop every now and then and see if there's any questions. Currently, everybody but myself is muted. So if you're trying to talk, I can't hear you. This webinar is also being recorded so you can watch it again later on. The Robofest coordinator, Shannon, will send out a link to that after we figure out how to get it to her and she gets it posted. All right. So once again, this is an EV3 software workshop. We're going to cover some of the basics of how to program your robot for this year's competition. And a lot more details. Definitely make sure you check the rule book for the Robofest rules, which can be found at the Robofest website. www.robofest.net and have you. All right, so we're going to review a little bit about the competition. This year's competition is called RoboHit. We'll look at some slides along the way as we go, or some videos from YouTube. The main purpose is to introduce what we're calling the SP bot and how to solve some of the challenges using the SP bot with this year's competition. So, video overview. So if we go to, oops, where am I trying to go with that? Sorry, trying to figure out how to adapt to the new thing here. New share, that's what I want. Right. I share my screen and I go back to Robofest. So you should all be seeing my web browser right now. And if I look, let's watch a perfect run here. So the robot gets started. The line follows along. It clears the blue block from the back side of the field. Clears the second block from the back side of the field. Clears the third block from the side of the field. Finds one of the trash objects. Hits the ball and pushes the trash object off the field. So the ball went through the upright, so that would be called a home run for this year's competition. Finds the second trash object, pushes it off the field. And returns home. So the easiest way to look at all these is just go to YouTube and type in RoboHit into YouTube, and you'll see a lot of our various videos here. So to give us a hint of RoboKit, no, you want RoboHit. So you should see all these Robofest videos. Feel free to watch those on your own at home. All right, let me get back to the slideshow. Give me a moment here as I figure out how to use our new software. All right, so our key task we're going to focus on is finding the playing field. So the playing field will be either a square or rectangular piece of vinyl on a darker background, and the robot is going to start off of the playing field some distance, all right, as defined, and that will be defined the evening or the afternoon of your Robofest event. We're going to talk about how to follow the edge of the playing field, then running the bases as we saw in that video, how to find the ball stand, all right, I call it the T-ball or the T-stand, and how to locate it. We're going to use some mathematics to find that. We'll then hit the ball off of it, off the ball. That's your task. That is the one thing we won't cover, is how to design and program a ball to hit the, or a robot so it'll hit the ball off the stand. We will talk about how to find objects and how to return home. All right, so like I just said, the actual batting of the ball is beyond the scope of this workshop. All right. The robot that we use for this workshop, and if you attended one of the on-campus workshops, we'll lend you this, but you can build a robot that looks like this for practice at home and just add to it for competition day. But if you notice, we have a light sensor over here, which is a color sensor acting in a light sensor mode. Off to one side, we've got another color sensor in the very center. The ultrasonic or sonar sensor, you could use infrared sensor, is facing sideways this year on the robot because it's going to be looking into the field as the robot line follows. We've got a touch sensor in the back. You could use that to start your robot if you wanted. And our right motor is programmed into port C, and our left motor is programmed into port B. Okay, let me fix that. All right, so then we got the left motor, once again, is connected to B. The right motor is connected to C. If your robot design involves your motors to be installed upside down, just remember when you set up your program, forwards will be backwards, and backwards will be forward. All right. Your color sensor, we've connected it to port 1 for sensor 1, port 2 for sensor 2, the touch sensor was in port 3, and the ultrasonic sensor we put into port 4. Also, the nice thing is, if you bought an EV3 or you even want to just play with the software, Lego does make the software available free following this download, www.legoeducation.com/download. You can also update the firmware to your robot that way. And then Dr. Chung has posted a link off over in the chat window on how you can download a PDF version of this PowerPoint and the example programs that we will use in this workshop. They're all found under the Tech Resources area of the Robofest website. And so if we go here, and we look at the Robofest website, right here, under Tech Resources, you will see right here is a PDF version of today's slides, and right here is the EV3 code. Okay, let me get back to the PowerPoint. Go, there it is. All right. An overview of the robot brick. Of the robot brick, all right, and how it works. Your status icon windows, you've got up in the top here, you've got something that tells you whether you're using wireless or Bluetooth. In the very middle here, you could have your brick name, all right? This one is named EV3, whether you've got a USB connection established, a battery sensor, you've got which program you're using, and other things like that. You've got number 1, the back button. This is also to use to back out of the menu system, or if your robot is running around uncontrolled and crazy, pick up your robot, hit the number 1 button, that'll stop it. Buttons 3 are for scrolling left, right, up, down, and button 2 is the center button. Think about it as like the enter button on your keyboard. And if you need help with that, watch some videos on the Lego website. Finding the playing field, our first task. All right, so In this particular game this year, the robot is required to start a distance, which in the rules is labeled as D2 from the playing field. So if you look at this down here, right, we've got a distance of D2 right here. All right, that's where the robot will start. May also indicate which direction the robot starts in the Robofest event. May have to face towards the field, away from the field, or left or right. May also be one of the challenges that happens at the event. You're going to have, in the home base, the starting place will have a foil tape on it. The third base over here will not have foil on it, and it'll have a block over it. Second base won't have foil, and it'll have a block covering it. First base will have a second piece of foil tape on it, and will also have another block on it. So one of your tasks is to run the bases and clear those little blocks off the bases to prove you've ran the bases. Also on the field will be two pieces of trash, one here and one here. They will be the same distance from the bottle, but they can be at random positions relative to the bottle. So, you know, they may be oriented like you see here at different random positions. The bottle, whether it's a rectangular field or a square field, will be in the dead center of the field. And to ensure that the judges always place the bottle in the same position, there will be a circle drawn there to do so. And if you look at the rules, there'll be some indications on, you know, whether the bottle was touched or pushed or anything like that. In the backfield area, we have the fence, and your goal is to hit the ping pong ball on top of the bottle hard enough that it'll clear this fence and go in between the two uprights. The poles will have a height, the fence has a height, and double check the rules for more clarification on that. So, our first task, finding the playing field. So assuming the robot is facing the playing field, we'd like the robot to drive forward until it reaches the playing field and stops. So if we look at our Lego bricks here, or our Mindstorm bricks here, this says that the motor is going to run here continuously. It's got 0 steering, in other words, it's going to go forward. It's got a power level of 50. It's using motors B and C. And the motor will run while waiting for some event to happen. And the event that's going to happen is we have our color sensor. And our color sensor here is it's a weight block waiting on the color sensor to do something. A greater than value of 40, and it's using the reflected light method here. Make sure that when you set this up, your icons look like this, all right? Reflected light, and it's a comparison value, and we're using the sensor plugged into port 1. So the robot will go forward until the light sensor sees a value recorded of greater than 40, and then it exits and executes whatever in the next block, which in this case is do a stop on motors B and C. So let's watch a quick video of what that looks like. Let me get my, oops, I lost my web browser. Give me a moment, please. Okay, and so here we are, task 1. Let's watch that real quick again. Robot just moved forward till it stopped at the field. All right, so one of the things you should do at home after you play with this program, run this program, which is available. We have on the tech resources, you can download this, and this is one of those programs. It will be labeled Fine Field EV3 right here, Fine Field EV3. So in the tech resources, when you download our EV3 program, you'll run that little sub-program within the EV3. The next thing is following the edge of the playing field. We're going to use simple line following here. So if you use the zigzag method to follow the edge of the playing field, the important thing is your robot's going to start off with the light sensor off the field. You're going to tell it, if I see darkness, i.e. I'm off the field, turn left. If I see brightness, I'm on the field, turn right. Off the field, turn left. So off the field, turn left. On the field, turn right. Off the field, turn left. On the field, turn right. And your robot will zigzag and wiggle waggle as it follows this line. So some key things we're going to need to find out to do this are, we need to know what values the sensor sees when it's off the field or on the field. And one way to do this is set your robot on the field while it's plugged in and communicating to your laptop. And let me share the EV3 software so we can look at that. Well, I don't have a robot plugged in, so we aren't going to do that right now. But if your robot is plugged in and you click on, let me get the pen back, so that you see this icon over in the bottom right corner of the EV3 programming field area or programming palette. You will get the things, and all sensors that are plugged into your robot, their values will display here. So port 1 sensor is reading 24, port 2 sensor is reading 21, the ultrasonic sensor is reading something at 32 centimeters away, and your motors are currently set at 0 rotations. So make a little note that on the field we saw 70, off the field we saw 10. So that's an important thing to take a note of. And we are using the reflective light intensity mode. So we're actually using the color sensor as just a light sensor. Okay, we want to know what is the median or the middle value of this. So 10. Okay, hold on a minute. I am having some technical difficulties. All right, so our average value is 40. So we're going to use 40 as our average value. And so if anything is greater than 40, that means we're on the field. Anything that's less than 40, we're off the field. So that's how we're going to program. So here's our simple line following algorithm. All right, there's the link to that video right down there. When you download the EV3 software that we put together for this webinar, the mini program you're going to run is line follow ZZ. And so let's see what that looks like as a video. Notice the robot wiggle waggles a little bit as it follows this line. All right, and obviously after it left the field, it kind of wandered off, but it was programmed to stop at that point. Okay, so let's look at how the line following program works. We have our sensor here. We have our color sensor is set to see a value of greater than 40. So if the value is greater than 40, this happens. All right, so if we're greater than 40, we're on the field and we turn to the right. If we're less than 40, we turn to the left. Right, so greater than 40, turn right. Less than 40, turn left. And we're only turning a little bit, a value of 15. And if you notice, this particular loop is a forever loop, and it's set to continue forever. right? So that's this little infinity sign. So there is no exit for this loop. So it's quite possible if you set your robot on a field like this, it might just follow it till the battery's died. Any questions at this point? Go ahead and type them in the chat window. All right, no questions. Now, there is, if you look it up, an improved line following algorithm, and it's called the 3-level line follower. The concept is listed here. We don't cover it in this seminar. It's one of those things to look up and learn on your own. But we just looked at the 2-level line follower. If I'm off the table.
Excuse me, how do you break the loop?
How do you break the loop? What do you mean by that?
In the line follow ZZ, how do you break the loop?
That particular loop is not broken. It just continues forever. We'll come to that in another slide on how to exit a loop.
Thank you.
All right, if you do use the microphone, please mute yourself again when you're done talking. Otherwise, if your dog barks in the background or whatever, the rest of us might hear it. Okay? All right, good question though. All right, so the 2-level line follower, like we were saying, is if I'm off the table, I'm going to turn right. If I'm on the table, I'm going to turn left. Well, that causes a lot of wiggle waggle, zigzagging, which also in the long run, because we're going to want to measure distances accurately, could add extra distance to your robot as it moves forward, because all that extra wiggle waggling will be counted by the rotation counters. The 3-level line follower says, if I'm definitely off the table, I turn right. If I'm definitely on the table, I turn left. But if such that my sensor sees that it's half on the table and half off the table, keep going straight, okay? And then that, and that. So you want to, so the best way to do that is to look that up via Google and see how that works. All right, and please do not annotate on the screen, because when I rotate to the next slide, all right, whoever has their microphone on, please turn it off. Whoever's talking to their child, please turn your microphone off.
I want to type, I don't want to speak. I want to type, you could use proportional lines. Oh.
All right. I need to clear all the annotations, because here's the problem. Whoever just scribbled on the screen, I can't get rid of that. So please erase your scribbles. And whoever did those 2 circles, please erase them. All right, well, we're gonna have to look at those circles the rest of this. Whoever put those 2 circles, please erase them. All right. All right, one method to move from one base to another is to use 2 color sensors. All right, sensor 1 will be used to follow the edge of the playing field. Sensor 2 will be used to locate the end of the playing field. There we go. All annotation is cleared. Excellent. Yes, Corey. Go ahead and type in the message area. Okay, let's look at how that works. So we got two sensors. Let's review that. Sensor 1 will follow the edge of the playing field. Sensor 2 will locate the end of the playing field. It's possible to achieve this using only one color sensor, but this is more difficult and less reliable. Remember that only 2 of the bases have foil tape, so we're not going to cover this, but something you might want to do is to add in a way to have your robot count how many foil tapes it sees, so you know which base you're on and whether or not you're between the home base and the other side foil. So our line following ZZ, we're going to modify that program to stop the robot when it reaches the end of the baseline. So this is how to break a loop. So we're going to use this program. The robot will line follow continuously. How can we make the robot stop when it reaches the next base? Well, we're going to look at it, but we're going to change this part here of the loop. So to exit the loop or break the loop, there are other ways to break a loop too within a loop, but this is the simplest way here, is to program when something within the loop sees or some action happens within the loop, it causes the loop to exit. So let's look at how we're going to alter that. So we once again have our line follower set up. When the light sensor in port 1 is greater than 40, that means we're on the field and we're going to turn right. When it's less than 40, we're off the field and we're going to turn left. And we're continually checking, this time sensor 2, to see if it's greater than 40 or less than 40. So that means when sensor 2 goes off the field and sees darkness, we're going to exit the loop and cause our robot to stop. So let's watch that quick video. Line follows. The front middle sensor sees the floor and stops. One quick replay of that. Okay. The nice part is at the same time, we also cleared the block off the field. All right. So this is line follow ZZ stop in our EV3 program sample we provided for you. It's a little mini program. Line follow ZZ stop is when you run around to do this. You can edit this to fit your robot as needed. Now, how do we find the ball stand? All right, so at some point, you're going to want to find out where the ball is so that you can move towards it and hit it. So we now know how to travel from one base to another, or one edge of the field to one corner of the field to another corner of the field. We know that the ball stand is halfway between 2 corners of the field. So we could use rules that are a way to measure the playing field and find it. So if we know that the field is 30 centimeters wide, and if we program our robot to travel half that distance, or 15 centimeters, we're going to stop in the middle. And once we've stopped in the middle, we can program our robot to turn exactly 90 degrees. And then we can travel forward towards the ball stand. Stop at a given distance again, which would be another 15 centimeters or so. And then program your robot to hit the ball, and away you go. So we're going to modify line follow ZZ stop to stop at the location of the ball stand, spin 90 degrees, and travel to the ball stand. So we're going to need a couple extra tools in our programming toolkit here. Line following. How do we measure the distance traveled, and how do we precisely turn? So the nice thing is we have our wheels are round, and if you think about some simple math, we can measure how far the robot travels with each rotation of the wheel. You can either do that using simple math or even another little program that we put together here to help you figure that out. Let's look at that program in a moment. Simple wheel geometry, right? So if you look at the circumference of a circle, which is the distance all the way around the circle, that is equal to the diameter of the circle times pi. And if we use 3.14 as pi, that works for us. Okay, and that'll help us calculate the distance traveled. All right, so let's look at that next. So for each rotation of the wheel, the robot will travel the wheel diameter times pi, or distance is equal to wheel diameter times pi times the number of rotations the robot traveled. So if you look at the side of your wheel, you might even see that some of them are stamped either at, might be stamped on the side of the wheel at 55. That means 55 millimeters, and 55 millimeters is 5.5 centimeters. So 5.5 centimeters times pi times the number of rotations will give us a distance. Well, if we take and just multiply 5.5 centimeters times pi, we get that our robot here that we used with a wheel diameter of 5.5 centimeters will travel 17.28 centimeters for every rotation of the wheel. So let's look at a video of this happening, and then we'll come back and talk about the program. Okay, and we see that it was 38.591, right? So that was how many, that was the distance the robot traveled there. All right, so let's get back to our PowerPoint and look at what the program that we have sitting here do. So this is measure distance. So this is a neat little program that tells you how far the robot traveled for a given amount of time. So if you look at this first block right here, this is a reset block. So this says motor port B. We're looking at the rotations, and when this little icon is shown, it says reset it. Just like in your car, the odometer, or the distance traveler in the motor, is constantly constantly counting how many rotations the motor has turned. So if you haven't, ask your mom or your dad to show you how the trip meter in a car works, and you can reset that to 0 to measure how far your car traveled. We have then set the motors in port B and C to operate and rotate while paying attention to time. They're going forward with 0 turning, a power level of 40, a time of 2 seconds, and then when they're done, they're going to stop. After we've moved forward for 2 seconds and come to a stop, we now are asking the motor port B, all right? And the other thing I want to comment on is, if you look up here at the top, each one of our programming blocks has a color attached to it. And let's just go real quick to the EV3 software and take a quick look at how some of that works while I'm there. So if you look at the EV3 software, let's go to line follow ZZ here. All right, it's up. So anything that involves let's go to the travel distance program. No. Line follow distance, object search, distance. All right, let's go line follows ZZ. So anything that involves operating the motors is found under this green area here, called action blocks. Anything that involves flow control or controlling timed events or looped events or whatever is under flow control, which is orange. Anything that involves a sensor is under the yellow area. Data operations or fancy math blocks are found under the red area. The blue area contains advanced blocks. So these do some more advanced features like file access, messaging, Bluetooth. And then at the very end, we'll talk about my blocks. And these are where you can take a more complicated set of blocks, condense it into a smaller my block to make your program look more efficient in the long run. And we'll come back to that at some point later. So we looked at how the robot moved forward, counted the distance. An important thing is if you're going to display something on the screen, and let's look at the use of the math blocks here. So we have a data wire coming out of the read rotations. That's right here, a data wire. And to connect a data wire, you're just going to grab this little tab here, you grab it over, and you drop it where you want it to go on the math block. We're using the math operation of multiply here. And so value A is whatever the sensor read for motor port B. Value B is our 7.25, which was our distance it traveled for run rotation. So number of rotations times the circumference of our wheel gives us our distance traveled. And so now what it does is it takes the value that got calculated, kicks it out into the display block, which is also another action block. It displays things on the screen. We just would grab this tab, drag it over here, drop it here. This is showing we've got text in a grid. The X value says it's going to be in the third row, third column. We want text size 2. And an important thing here is if you ever display things on the screen, you have to give some sort of weight. If you don't wait, it will flash onto the screen for like a millisecond or two and clears the screen before you can read it. So this is why we have the touch sensor. So that value will be displayed on the screen while we're waiting on something to happen. We're using the touch sensor plugged into port 3, so that value stays displayed on the screen until we touch the touch sensor in port 3. Now, to compute the distance to travel along the edge of the screen, we're going to take either our length or our width, whichever one you feel like using, divide it by 2. And so like I said, if our field is 50 centimeters wide, we need to travel 25 centimeters to get there. We're going to compute the number of rotations to travel that distance, follow the edge. When we've traveled that distance, or that number of rotations, we exit our loop, we spin 90 degrees, and then travel again another set distance to hit to the bottom. So let's look at that. So here, we're assuming our field is 80 centimeters long. 80 divided by 2 is 40 centimeters. So our number of rotations, so if we look, distance is equal to wheel diameter times pi times rotations. If we do a little bit of algebra, in other words, we divide both sides by wheel diameter by pi. So our distance divided by wheel diameter by times pi, we get the number of rotations we need to travel forward for. So 40 centimeters divided by 5.5 centimeters times pi, or our 17.28 that we had earlier, tells us that we need to travel for 2.32 rotations. If we travel 2.32 rotations, we should be in the middle of the field. So, line follow and stop after following the proper distance. So, line follow with distance EV3. So, we're going to have to count number of rotations to stop. So the first thing we need to do reset motor B. Then we're going to do our standard live following loop, right? If we're greater than 40, we're going to turn right. If we're less than 40, we're going to turn left. And we're going to keep doing that while line following. The exit condition on the loop is when motor port B is greater than or equal to 2.32 rotations, we stop. So let's look at what that looks like as a video. Hold on, something just went funky on me here. There we go. I'm having difficulties with the software right now. Hold on a moment. There we go. All right. So we moved forward half the distance to the field and stopped. Okay, so move forward half the distance to the field and stopped. So now, once we've stopped there, we're in front of the bottle, or next to the bottle, I should say, or wherever position we need to be. We need to turn exactly 90 degrees, so we're either facing the bottle that we want to hit or the piece of trash that we want to move, whichever you've decided you want to do. And so we want to start with our robot facing east and rotate it so that we're now facing towards where we need to be facing. We're going to use the spin feature of the robot to turn the robot. And when the robot spins, the pivot point of the robot is right here in the middle. So the center of the robot should stay over the same point while the robot just kind of spins in a circle. So if there was a dot right underneath the axle of the two wheels, that the middle of the robot right there between the two wheels would stay there. And the diameter of the track is the width of the robot. All right, so to spin the robot 90 degrees, the robot track width, in other words, the distance between the two wheels, is 16.2 centimeters. So the circumference of this circular path is pi times that diameter, so 3.14 times 16.2 centimeters, gives us a circumference of 50.87 centimeters. The circumference of the robot's wheel was 17.27. So, and a 90 degrees of a circle is 1/4 of the circle. So 50.87 times 1/4 gives us a distance that our wheel needs to travel is 12.72 centimeters. So how many rotations to travel 12.72 centimeters? Well, rotation is equal to distance divided by wheel circumference. And so 12.72 divided by 17.27 gives us 0.74 rotations. So what we need to do then is have another loop, but instead of moving forward, we'll just have a spin in there to set it up for 0.74 rotations. So here's a simple block. So after your loop, you would add this block right after your loop, and it just says spin 90 degrees. So let's look at that as a video. The robot spun 90 degrees and stopped. And this is labeled Spin 90 EV3 in the programming software we've provided. So assume that we need to travel 40 centimeters to get to the center of the field. So modify line following EV3 to travel the same distance in a straight line. All right. So, and this was found on slide 31, the number of rotations we needed to follow for that distance. So instead of even just following a line, if I want to travel straight for 40 centimeters, I just use this block here of motors B and C, no turning, power level of 50, and after 2.32 rotations, I stop. And notice this part of the block is important. This is saying that the motor is controlled by the number of rotations. That's what this little symbol right here says. The motor is controlled by that many number of rotations. And we have this under travel distance EV3. How do you find an object? All right, let's take a short pause right now. If anyone needs to get a restroom break, and we'll be back in a couple minutes. Let's make it 5 minutes, a 5-minute break. All right. I think we get All right, so I've got a question from AJ. How do you make the EV3 do all these commands together? So let me switch over to the, so AJ, before I start talking, let me verify you are here. If you're here, give a quick type in the chat. All right, so AJ asked, how do you get the program to do these things together? So let's go to a screen share of the EV3 software. Let's see, I will do line follow distance. So, and then let's go to spin 90 degrees. So I'm gonna just make life easy. I'm going to edit, I'm gonna copy the spin 90 here. Okay, and then if I go to line follow distance, and I'm going to go edit, paste, and that puts that block in there. So now if I put the line, the spin 90 after the loop here, so now I'm going to line follow a distance and then spin 90. So the easiest way to have it do multiple things is do this operation. All right, actually, I would probably want it to stop, so I would put it afterwards. So what it does, this says I'm going to line follow, do some distance, I'm going to stop, and then I'm going to spin my 90 degrees. Then after spinning 90 degrees, I could say then, let's see, move, whoops, not, yeah, so then I could say move forward. Where'd that block go? Oh, I lost that block. Move forward, some extra distance, and I want the hand so I can move things over. All right, and then I'm going to change this to number of rotations, and I want back to the arrow. All right, there we go. So then I can change this to, let's say, 3 rotations, right? Or whatever I wanted it to do. And of course I need to make that B and C. I think I have the wrong motor there. I wanted to move steering, so let's change that out to move steering. And I'm going to delete that block. I grabbed the wrong block. There we go. So number of rotations, and let's say I wanted it 4.3 rotations. All right, there we go. So by chaining the blocks one after the other, you can have the robot do this action, stop, do that action, stop, do that action, and goes from there. So let me get back to the PowerPoint. And where's the chat? Where'd the chat go? So AJ, did that answer your question? All right, then Viva has asked, when will objects be unveiled at the competition? So when you get to a Robofest competition, usually what happens is you have about an hour or so to get things set up, get your robot set up. You can play on the field and experiment. And then at the start time of the event, everyone will be announced, and you'll have about 30, so all the unknowns will be announced, and you'll have about 30 minutes to make any changes to your robot that you need to change to be ready for the event. And then after that 30 minutes, all the robots will be collected to impound, and you have to turn all your robots in. They'll be inspected to make sure they fit any size or weight or any other dimensions that are required by that year's competition. And then some order then via some order devised by the site host, teams will be called up and be allowed to compete. Remember, your robot has to get all this done in less than 2 minutes. And then the scoring sheet at the end of the rule book will tell you how it's scored. All right, any other questions? All right, so let's look at how do we find an object. Okay, oops. Let me get back to the chat so I don't totally hide it. Okay, so finding objects. So we have an ultrasonic sensor on the side of our robot. And it sends out a sound pulse, listens for echoes to come back from objects. And from those echoes, it kind of says, yes, there's an object within the distance I'm searching for. And it can even tell you how far away that object is. But if you look right now at the screen we have here, one of the interesting things about the ultrasonic sensor is it doesn't see in a nice straight line. It sees out in a cone. So if anything is within this cone of vision for the ultrasonic sensor, it will pick it up. So ultimately, it could be seeing all three of these objects. Now, you could say look for an object that is, if you know that the ball is at 40 centimeters, you could have your ultrasonic sensor looking for things that are less than 38 centimeters. So it won't see the ball stand, but might see the trash object. So remember, your robot will be line following along the edge of the field, using the ultrasonic sensor to look for the objects and do them. So there's a couple different ways. You may, from at the beginning, like we just talked about, know where the object is located because it's been announced, and you can program your robot to travel that distance. Or you can have your robot find the objects by knowing they're a different distance than the ball stand. So let's look at some of the ways we can look at that. So we travel around the playing field. We know that trash objects will be closer to the robot than the ball stand, at least from one side of the field, right? Because like, let's say the trash objects are here. Well, if I'm here, the ball stand is closer. But if I'm here, trash object 1 is closer. And then if I'm here, trash object 2 is closer, all right? But the important thing is the trash objects will always be, at least on the square field, less than the distance of the ball stand. Think about that. So if the robot is here, it sees trash object 2. If the robot is here, it might see trash object 1 and the ball stand, and it might not distinguish how far they are away from each other very well. But once again, if the robot comes over here, it sees trash object 1 as being really close. So this is one of those things where you're going to have to set up a practice field at home or at your school and experiment so that you can find the trash objects and not the ball stand. It's going to take some experimenting. And that is why it's called computer science. There's experimenting involved. So we're now going to travel from one base to the other and stop if we find a trash object. Now, if you notice here, we got our standard line following program, but now the exit condition for our loop is if the ultrasonic sensor here sees something that is a distance of less than 25 centimeters. And remember, we got it plugged into port 4. So when we see something at less than 25 centimeters, we're going to stop. All right. We know the distance of the ball stand, so we need to check the distance threshold to ensure the robot sees the trash, not the ball stand. All right. So remember, the trash object is always going to be there. And this is located under Object Search, EV3. But let's watch this as a video. Okay, so it travels along, goes past the ball stand, and stops at the cup. Now, let's go back to that and back it up just a smidge. I want to stop something here. Notice that where the ultrasonic sensor is located, it's actually looking behind the cup. Because remember, that cup, it sensed it when it was the edge of that cone that we looked at, that the ultrasonic sensor sees with. And so if you turned here and went forward, you very well might miss the cup. So you may need to program in, after I've seen the cup, I need to go a smidge further, like maybe a 1/10 of a rotation or so, to make sure I'm actually lined up with the cup. Because the ultrasonic sensor, remember, has that cone of vision, and it's stopped before the cup. Okay. So, batting the ball. So, this is beyond the course. This is one of those things we want you to experiment with. But some of the key things to pay attention to while thinking about this. You should be able to position your robot in a proper hitting position using the techniques outlined in this course. Now, since your bat is you may want to hit the ball from the side of your robot. You may not want to aim directly at the ball stand. You might want to go to the side of it. And to make sure that your bat hits the ping pong ball really far, you want your bat to spin really fast. All right. Your EV3 motor has a rather small speed. So if you go to a medium motor, you get faster speed. And that's because the gearing ratio, that has a lot to do with the gearing ratios built within the motors themselves. Or you might want to play with the gears that come with your EV3 kit. So if you've ever ridden a bicycle with gears on it, if your front wheel is on a big gear and your back wheel is on a small gear, for every 1 rotation of your pedals, you might do 5 rotations of your back wheel. So that we always think of as power to speed. So on your motor, you might want to have, as we call it here, the drive gear, one of the 2 big gears, all right? And then on the output motor, the one holding the bat, you might want to use some of these smaller gears. And so we can multiply the speed here. So the drive gear divided by the driven gear, all right, number of teeth on each, gives us our speed multiplier. So if we got 36 teeth on our drive gear and 12 teeth on our driven gear, 36 divided by 12 is 3, so 3 times our input speed. So if our robot, let's say doing 3 meters per second, and I do this gearing ratio here, my robot would now be doing 9 centimeters per second, right? 3 times faster. So playing with some gears may help you hit the ball faster, and thus it'll travel further because the ball will leave the bat at a higher speed. Returning home, task 6. So to get a perfect score in Robofest, after you've cleaned all the blocks off of the 3 bases, you've cleared the 2 pieces of trash from the field, and you've hit the ping pong ball between the uprights, your robot needs to come back to the home base, which is one of the pieces of reflective tape, all right, should be defined at the Robofest event. You need to make sure you get there. So we're going to modify the line following program to follow the baseline home until the reflective tape is found. Key thing here, though, remember we've got 2 pieces of reflective tape. One is first base and one is home plate. So, other thing to pay attention to is we will be using a white vinyl playing surface. It's very white, it's shiny, and the silver tape is also pretty shiny. So to make sure that your robot can distinguish the distance here, we found that if you leave about 15 millimeters or 1.5 centimeters distance between the bottom of your sensor and the playing field, that allows for the light differences to show up between the playing field and the silver tape. So here is a thing we've got going on. So line follow ZZ home, and let's look at that as a video. So we knew we were at that base. We've line followed. till we got home, and we stopped. Let's watch it one more time. We line followed till we got home. Okay. And then we stopped, all right? And we're checking for home plate. And the exit condition here is the silver tape is highly reflective. So you're going to find out that when your light sensor is over the silver tape, you might see a value of like 80 or 90 for the light value. So when we're greater than 90, we stop. Remember, the white field was 40, or it was 70. The silver tape is like 90. So there is a difference, but it might not be that great. But there will be enough for you to differentiate silver tape versus white field. And that's going to be one of the things you're going to play with. Another thing to pay attention to is the way your light sensors behave at home or at your home school may be different than the way they behave at the Robofest event site. So give yourself some time to reset your sensors at the Robofest event to adjust for the lighting conditions of the day. Also, if the event site has open windows, the sunlight coming in from those windows will affect your light sensors. Some of the teams build in, and you might want to look at how to do this. There's lots of videos out there I'm sure you can find. They actually calibrate their sensors with a little mini program or the beginning of their program when they come up to the Robofest playing field. So they set on the field, press a button, it reads the white area, set it off the other, it reads the dark area, and then they tell the judges they're ready to start. But you better be able to do that quickly, because if you take too long, you might get a time penalty. All right, so the solving this game might get pretty complicated, because remember, we're going to be chaining together a lot of blocks together. And this could get difficult. So very large programs can become difficult to understand, navigate, and use. So if we take a bunch of blocks and condense them down using the My Block Builder to create custom blocks, that one My Block can be used to replace another bunch of blocks, and it makes your program look easier to read and follow. So let's look at how some of that might work. So we've got all these blocks here today. We've got this section of code, right? It's the move forward until the edge of the playing field is found with color sensor 1, and then stop, and then after stop, rotate 90 degrees. Well, this is a piece of code. We might want to just reuse it over and over and over. So if we use My Blocks, we can convert this into a single block. So creating a My Block. So you're going to highlight all that code, go up to the Tools menu, select the My Block Builder, enter the block name and description, select an icon for it, and hit Finish. So let's look at the EV3 program and do this. So I'm going to take the line follow ZZ home and turn it into a My Block. So I highlight this loop. Okay, I go up to Tools, My Block Builder. Oops, I highlighted the start block. You can't highlight the start block. That's this little green one at the beginning. Okay, Tools, My Block Builder, and I'll just call it ZZ Home. Line follows home, and find an icon here. I like this little red thinking head here, and I go Finish. So notice line follow ZZ home has now become a My Block. If I want to find it also again, I can find it down here, and if need be, I can double click on that block and it re-expands it. So I could, once I've double clicked on it and open it again, I could edit it, make some changes here, and it'll resave it. So now, like, let's see, where'd it go? Line follows easy stop. Is that the one? Where'd it go? Line follows easy. I forgot where it went. All right. But that's how you create a My Block. So let's go back to the PowerPoint. And if you need to review that, I'm sure on YouTube there are some videos that'll walk you through it again. So, key things we learned in this course today is, how do you find the playing field? Because remember, you're going to start off with a playing field. Now, we assume the simplest case, you're facing the playing field, but maybe if you're at an angle of the playing field, you might need to turn 90 degrees to face the playing field, then move forward. We've looked at line following, all right? We looked at how to run the bases, how to find the ball stand, find objects. We hinted at how to bat the ball, returning home in My Blocks. All right. Some sample move block problems, so some things to look at. Using one move block, make a robot travel 50 centimeters forward and assume your tire has a diameter of 4.32 centimeters, right? And so we would have to move 3.9 rotations. So this is a experiment you can try at home. Make sure your robot moves exactly 50 centimeters by measuring while playing with this. And like I talked earlier about the wheels having a stamping on them. So if you look at the side of this wheel, right over here somewhere, it'll tell you the diameter of the wheel, right? And be careful, it tells you the diameter of the wheel in one measurement, and it tells you the width of the wheel in the other. Okay. And then make your robot, instead of turning 90 degrees, make it rotate clockwise 180 degrees. Okay, so these are some things at a Robofest event we had the students try in front of us. So, are there any further questions before we're done for the night? If there is a question, go ahead and type it in the chat area. If not, I'm going to thank you for joining us tonight. This video will be posted probably tomorrow sometime. And Shannon will tell you how to get to it. By the way, also, if you have any further questions, feel free to type the Robofest office, or you can contact me. And we can always meet up via Google chat window to go over some of this stuff. Right, we had a question, how do we download this presentation? All right, so if you go to robofest.net and look on your tech resources, there will be a PDF version of this slide. It's under tech resources. Training for host sites. Eric, I'm going to give you microphone.
Basically, this is the first time we've used we've been a host site, and just trying to figure out the game plan of hosting.
Where do you live?
This is in Rochester.
Oh, so you're here in Michigan.
Yep.
Oh, well, the easiest way then would come down and talk to us at Lawrence Tech, and we'll talk to you through it. When is your event?
March 18th.
March 18th. Is that a Friday or a Saturday?
Saturday.
Okay, I'm not available that night. If need be, yeah, come down to Lawrence Tech, talk to us through it. We'll help you out. I could come up there Friday the 17th and run you through some things. Generally, we can also make sure, especially for you, that a Robofest liaison will be there to help you out. I'll just be in Kalamazoo that day.
Okay. There's certain things like, okay, like color of gym floor and such, but I imagine you need enough contrast for the robot to see things.
Well, often what we'll do with that is we have the white vinyl sheet, and then we might have a black paper or black
Background.
tablecloth, black,
Okay.
whatever, so that if your floor is really random colored or odd like that, we put an extra width of black surrounding the white, which takes care of that problem.
Okay. So maybe what I'll do is I'll take pictures of the venue and such, and then get that. I plan on coming up on the 18th of February for the training session.
Oh yeah, the warm up. Yeah, yeah. So yeah, everything you need to ask, then ask it. We can help you out on that day. That's probably the best way to have all your questions answered.
Okay. Appreciate it very much.
Yeah. Nice thing is you're local, so
Okay. Thank you.
not a problem. Any other questions? Okay, cool. And hopefully I'll see some of you at a Robofest event. Have a good night, all.